Hello students, the topic of this session is binary codes. As we have seen in the keyboard, there will be numerous kind of data that we have seen on the keyboard. Keyboard characters like the alphabetical characters from A to Z, the digits from 0 to 9, or a special character like plus, minus, star, dollar symbol, ampersand symbol, even the space that you provide using space bar key. All these special characters are called as the data. Using keyboard, you are going to input only these kind of data like alphabets, digits, and special symbols. And these symbols, which we recognize it as alphabets, numbers, and special symbols, systems take it as in the form of bits, that is 0 and 1. The bits 0 and 1 must represent any data internally. Hence, computers use binary coding schemes to represent data internally. In binary coding, a group of bits represents every symbol that appears in the data. Group of bits, 8 bits to one group na, we call it as a byte. To indicate the number of bits in a group, a byte is referred to as n-bit byte, where the group contains n number of bits. The term byte commonly means a 8-bit byte because modern computers uses 8 bits to represent one symbol. See here, this is the ASCII code sheet. Here you can observe for each and every character there is a machine language. All the keyboard characters are present in the first column, numbers or digits from 0 to 9, all the special characters, alphabetical characters have been written here, and in front of those characters you have some series of zeros and ones. You can observe that in the second column, that is called as the ASCII code. It's a group of 8 bits. You can observe that you have 4 plus 4. It's grouped into 4 plus 4 set of bits, that is totally it's 8 bit. If you press 1 from your keyboard, 1 is represented as 0011110001 for a computer. It's called as 1, numeric digit 1 for us for using the keyboard, and for the computer it converts that 1 into this series of 8 bits. That is for 1, that's an example that I have taken. For 1, just the number 1 converts into series of bits. For the capital letter A, you have 0, 1, 00, 0001. This is the kind of machine language that system uses. It converts every piece of information that you are entering through keyboard into this kind of 8 bits. That is what it is given here. That combination of 8 bits is called as a byte. Next, coming to BCD code. How does it makes a conversion process? Here we have different methods. One such method is BCD or binary coded decimal. It is one of the early computer codes. Each digit of a decimal number is represented by its binary equivalent. It converts decimal value to binary number according to the table which is here. It divides the given number by 2 and makes the conversion process possible. According to the table, here you have a digit 1. The BCD equivalent of 1 is, if you press 1, computer in the BCD equivalent form accepts it as 0001. It adds some more 4 set of zeros to it and consider it as the number 1. So how can we convert this decimal number into this BCD equivalent? Is by dividing this number by 2. If you divide the number 2 by 2, you will get 2 sets of remainder in binary language. For example, if you divide 2 by 2, 2 ones are 2, the remainder would be 0. So if we go in a reverse order, we write it as 1 0. Preceding to this, we had the numbers 0 0. So this is the BCD equivalent of number 2. So I am going to write this number here, 0 0 1 0. You cannot divide 1 by 2. So you keep it as it is because it's just a matter of 1, and here also it's only a matter of zeros. Next, divide 3 by 2. If you divide 3 by 2, 2 ones are 2, remainder would be 1 here. So if you take it in the reverse order, 1 1, append zeros here. So 0 0 1 1 would be answer for this, and divide 4 by 2. 2 2s are 4, remainder is going to be 0. Divide once again until you get 1 or 0 as the answer. 2 ones are 2, result is going to be 0. So write in the reverse order, 1 0 0. Since we need 4 bits, append it with 0. 0 1 0 0. Next, 5. Decimal number 5. 2 2s are 4. Remainder is going to be 1. 2 ones are 2. Remainder is going to be 0. So we have, if I take it in the reverse order, 1 0 1 here, append it with 0. So 0 1 0 1 is going to be the answer. Similarly for 6, again divide by 2, because the base of BCD or binary is 2. 2 3s are 6, remainder is 0. 2 1s are 2, it is going to be 1. So here answer is 1 1 0. Append with 0. So 0 1 1 0. For the digit 7, 2 3s are 6, remainder is 1, 2 1s are 2, remainder is 1. So for 7, it's 3 1s preceded by 0, 0 triple 1. For 8, 2 4s are 8, remainder is going to be 0, 2 2s are 4, remainder is going to be again 0, 2 1s are 2, it's going to be 0. Here we are going to get 1 followed by 3 zeros. Similarly, if you divide 9 by 2, 2 4s are 8, remainder 1, 2 2s are 4, 0, 2 1s are 2. So 1 0 0 1 would be the answer. So this is the BCD equivalent of. There will be hardware circuits that are going to convert whenever you enter these kind of numbers. It will be entered into the circuit. Circuits converts these numbers into this form. This is the BCD binary coded decimal technique of converting the decimal numbers into BCD format. Coming to, there is another method called as 8421 code. Coming to this 8421 code method, write 8421 here, this number, sum of these individual numbers, and you are going to get 15 as the answer. That is 8 plus 4, 12, 12 plus 2, 14, 14 plus 1, 15. Now I am going to write only zeros for the first step. For the decimal number 1, I am going to highlight only this position, and I do not need these positions, so I am making it as 0. Why I am making these 3 as 0 is I do not need it. Since I am representing the decimal number 1, I need to enable only this one. So it has created a set of values, that is 0001. This is another method. You are going to get the same answer. For decimal number 2, again in the 8421 code, I need only this number now. Enable this one, disable this one. Here also you are going to get the same answer. For decimal number 3, here we do not have decimal number 3. So since we do not have 3, add the numbers from which you are going to get the number 3. If I add these two, I will get 12. If I add these two, I will get 6. These two numbers would give me the result 10. If I add these two numbers, I am going to get 3. So highlight these two things and make the remaining things 0. So answer is 0011. Again 8421 code. For the number 4, 4 is already here. I am making the remaining things 0. So answer for 4 is 0100. If you divide by 2 also, you are going to get the same answer. You can match these two columns. Similarly, you can replace the numbers using 8421 code. for the number 9. If I add 8 plus 1, I am going to get 9. So highlight only those things. Make remaining bits 0. That is 1, 0, 1. You can fill it up these things in a similar manner. Coming to gray code. Decimal to gray conversion. We have already learned binary to gray conversion. Just write the MSB bit and XOR each and every value. For this one is 0 itself. Write the MSB main significant bit, apply XOR. 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. In all the conversion methods, we have the same answer. These are just the different way of converting. Next, 0 XOR, write the significant bit. 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 0, 0 XOR 0, that is 0. 0 XOR 1, that is 1. For 1 XOR 0, 0. The gray representation is going to be different. Here you have 1 0 as 1. Next, write the main significant bit 0 for the number 3. 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 1 is going to be 0. Next, main significant bit 0 XOR 1, 1. 1 XOR 0, 1. 0 XOR 0, 0. You can complete these things.